Welcome back. So I'm pretty excited. We are starting to get into my favorite material in differential equations, which is specifically how we can relate differential equations and linear algebra. So in the last few lectures, we've been talking about these higher order ordinary differential equations. What I mean by high order is that we have many, many derivatives of our state x with respect to time. So not just first derivatives x dot or second derivatives x double dot, but nth derivatives, in this notation here. And today, what I'm going to show you is how to turn this high order ODE with a lot of derivatives into a coupled system of first order ODEs. So specifically, we're going to turn this into a system of coupled first order ODEs. And what I mean by first order is this is going to be a system of n coupled first order ODEs where each of those equations, each of those ODEs is only going to have first derivatives with respect to time. So this might be easier. I'm going to show you, in fact, it is a lot easier to solve these systems of coupled first order ODEs than their equivalent higher order representation. These are totally equivalent, but this is where we usually like to work computationally on computers, even pencil and paper. Everything is easier here. I'm just going to jump in. This is an important lecture, so pay attention. And then the next few, we're going to start talking about eigenvalues and eigenvectors, some of my absolute favorite material in all of applied math. I think you're going to love it. Okay, so what we're trying to do is take this high order system and write it as a matrix system of first order equations. And we can do that pretty simply by introducing new variables. So we introduce new variables. So currently, the only variable we have here is x, and now we're going to introduce some new variables. I actually opened up a new pack of markers because I'm so excited about this lecture. And so we're going to say our first variable is just our original state x. Our second variable is going to be x dot, the first derivative of x. x3 is going to be x double dot. You see the pattern here. All the way down, I'm going to have n of these variables. So I have an nth order differential equation. And so I'm going to write this in terms of n coupled first order equations in these new variables, where my last one is the n minus 1th derivative, the n minus 1th derivative. Okay, so this is my new state vector that I'm going to be dealing with is this x1 through xn, where each state in this vector represents the state, my original variable x, and all of its derivatives up to n minus 1. And so specifically, I can write down a pretty simple differential equation or system of differential equations. So what we're going to write down is, of course, x1 dot is literally just x dot, and x dot is x2. So we say x1 dot equals x2. I'm going to repeat this one time, very important. We're going to take the ddt of each of these variables. We're going to figure out what x1 dot, x2 dot, x3 dot are, and then we're going to represent those in terms of x1, x2, x3, and so on and so forth. We want a closed form system of the derivatives of all of these states as a linear combination of those n states. So I start with x1 and I compute x1 dot. x1 dot is the time derivative of x, x dot, which is my second state, x2. So x1 dot equals x2. Similarly, x2 dot, if I have x2 dot, that's x dot dot, or x double dot, which is my state x3. And so on and so forth. So xk is going to be, the ddt of xk is going to be xk plus 1. And that works all the way for all of these rows until the very last one. So let's say x3 dot is going to be x double dot another dot. So the ddt of this x double dot is now x triple dot, which is going to be my x4 state. So x4, and so on and so forth until this very last row equation, where now I'm going to have xn dot. the time derivative of this state is the time derivative of this. And if we add one more derivative to the n minus 1th derivative, we get the x to the nth derivative. This equals the nth derivative of x, which is specifically, can I just make my life easier for one moment? Please bear with me. I'm going to divide all of these coefficients by an. That's totally fine because I can divide all of my coefficients by an, and these are just new coefficients, and it still equals 0. I'm going to get rid of that here real quick. And so now when I'm trying to do this last row equation, xn dot, which is the nth derivative, it equals all of this stuff moved over to the right-hand side. The nth derivative equals minus all of this stuff here. So this literally equals, I'm just going to do it. It's minus all of this stuff, minus a naught x minus a1. So x is just x1, so minus a naught x1, minus a1 x dot, which is x2, minus a1 x2, minus a2 second derivative is x3. I just want to be very careful. Minus dot, 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 minus a n minus 1 times the n minus 1th derivative, which is my xn. Okay, I think this is correct. I'm going to just look at my notes. That looks like I got it right, and there's minuses on all of these. Okay, so I'm not completely convinced that at this point, or maybe you shouldn't be completely convinced at this point that I've actually done anything to simplify my system, but very soon I will hopefully convince you that this is actually much, much easier to work with. So what I'm going to do now, and I think I'll switch to blue here, is now what we're going to do is we're going to be able to write this whole system of equations. I want to make sure I have enough space here. I can write this as d dt of my vector x1, x2, x3, dot, 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 all the way to xn. This is going to be a big matrix times my vector x1, x2, x3, all the way to xn. So it's going to be some big matrix, and I want to make sure to give myself space here, so I'll go all the way up to the end. A big matrix times x1, x2, x3, dot, 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 xn. Okay, and I don't want to be sloppy here. xn. Okay, and so this is really easy to read off what the terms of this big matrix are. x1 dot equals x2. So that is 0, 1, 0, dot, dot, dot. You know what I'm going to do here is I'm going to add one more row. Should I add one more row for the xn minus 1? I think I'm going to. I think you're going to thank me later if I add one more row for xn minus 1. I'll make this a little bit more concise. So xn minus 1 xn. Okay, this is going to go down to xn minus 1 to xn. Good. And now this big matrix here. Okay, so the x1 dot term is x2, which if I take this and I multiply it over, this is kind of the the x1 spot, the x2 spot, the x3 spot, dot, 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 xn minus 1 spot, xn spot, if I multiply this whole thing over. So x1 dot equals x2, so that's 0, 1, 0, dot, 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 0, 0. Easy, easy, easy. x2 dot is x3, so similarly that is 0, 0, 1, dot, 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 zeros everywhere else. The x3 dot is x4, which is 0, 0, 0. The next column would have a 1 in it, but I don't have it written here. Dot, 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 0, 0. Okay, just not mess anything up here. And now the xn minus 1th derivative, ddt of this, is xn. So I'm going to have zeros everywhere here up until the very last entry. So ddt of xn minus 1 should be xn. And that is, in fact, what I get if I multiply this. So far, most of this matrix is almost trivial. It's mostly zeros, and it has one diagonal of ones saying that x1 dot equals x2, x2 dot equals x3, x3 dot equals x4, dot, 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 xn minus 1 dot equals xn. And all of the action, all of the interesting stuff in this differential equation, all of these coefficients enter in this last equation. So this xn dot is minus a0 in the x1 minus a1 x2 minus a3, no, a2, sorry, I really should be careful here, minus a2 times x3 dot, 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 minus a n minus 1, yeah, minus a n minus 2 times x n minus 1 and minus a n minus 1 times xn. So you can kind of convince yourself, just go through the motions, take this vector, knock it on its side, multiply it by this, and convince yourself that that's equal to this equation here. And in fact, all of these equations are represented by this matrix system of equations. So now this is actually something that we can really work with. This is linear algebra. We can, I'm going to show you in the next few lectures, we can solve this system in closed form by finding the eigenvalues and eigenvectors of this matrix. We can integrate this numerically way easier than working with this object here. Even if I wanted to find the roots of the characteristic polynomial, the best way to do that is to find the eigenvalues of this A matrix, which I'll show you in a minute. So I'll just write this and kind of summarize this whole thing here. You can write as a big vector x. This is, I'm going to use the notation that an underbar means that this is a big vector of states x. This is literally underbar x equals, x1, x2, x3, dot, 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 xn minus 1, xn. That's what this underbar means. And so this x vector dot is equal to this big A matrix, times x. So this is a matrix system of equations. They are coupled because x1 depends on x2, and x2 depends on x3, and dot, 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 and xn depends on all of them, so it's coupled. It's coupled. There are n coupled first-order equations because I'm only taking a single time derivative of any of these states. Now, of course, morally, we know that these states represent higher derivatives of my original variable x, but here we have transformed the system so it's simpler. So I'm only dealing with first derivatives of a larger dimensional, a larger state x, underbar that has n components. This is a vector, this is a matrix A, and this is another vector. So this is a huge deal. This, we are going to spend most of the next, I would say, 4 lectures, maybe 5 or 6 lectures now dealing with this matrix system of equations, because this is where linear algebra and differential equations meet. So this is where, linear algebra and differential equations, diff-EQ, this is where they meet, and it is wonderful, okay? So this matrix system of equations is where we're going to use all of our powerful techniques from linear algebra to solve really interesting systems in differential equations. And for me, this is the high water mark of applied math, really, is when we start analyzing these systems and understanding the real world in terms of both linear algebra and differential equations. Okay, good. That's the main thing I wanted to show you, is how you can take any higher order system and turn it into a coupled system of first order equations, which gives you this matrix system of equations. What I think I'm going to show you for the rest of this lecture, because I do have a little bit of time, is the next thing I'm going to show you, this is very important, is that the eigenvalues of A, this A matrix, are the roots of the characteristic polynomials, are the roots of the characteristic polynomial. And these mean the same thing, essentially. I've shown you before that this is true. Oh, polynomial, sorry, it got cut off. These are the roots of the characteristic polynomial. Let's just call it poly for short. We're friends. Polynomial. And I've shown you this for a second order system before, and so now I'm just going to, again, convince you that the eigenvalues of this A matrix are equivalent to the roots of this characteristic polynomial. Okay, so I can my eigenvalue equation for how I solve for the eigenvalues of A, that eigenvalue equation is my characteristic polynomial. I'm going to erase this, and I'm going to show you that. Just stay put. Okay, so we have shown how you take this system and, this high order ODE and turn it into a system of first order ODEs. And I claim that the characteristic polynomial of this equation is the same as the eigenvalue equation for this A matrix, this big matrix here that relates all of these states. And specifically, the eigenvalue equation, the equation you use to find the eigenvalues of A, so the, I'm just going to use for short, we call these the eigs, sometimes the eigenvalues. The eigs of A are specifically those lambdas, are lambdas that satisfy this equation, determinant of A minus lambda times the identity matrix equals 0. Now I'm going to derive this from scratch in a couple of lectures very soon, specifically as a set of lambdas that you need to solve this differential equation, So if this looks like a bunch of hairy math that came out of nowhere, it is, but I'm going to derive this in a little bit. Just take for granted, not granite, take for granted just for the moment that this is the expression that you use to solve for eigenvalues of A. Okay, this is how you find the eigenvalues of A, is you find the lambdas so that the determinant of this matrix equals 0. Okay, and I'm just going to show you on an example. So the example I'm going to do is, let's say example is, I'm just going to do this up to third order. So I'm going to say I have ddt of x1, x2, x3, and we know that this is going to be 0, 1, 0, 0, 0, 1, and then minus a naught minus a1 minus a2 times x1, x2, and x3. And of course, this is the matrix system representation of a third order ODE that I'll write out here. So this third order ODE would be x triple dot plus I guess a2x double dot plus a1x dot plus a0x equals 0. So I hope you believe and have been convinced that this equation in green and this system in blue are completely equivalent. This is just what happens when you suspend variables and write this as a coupled system of first order equations. And so I claim that the characteristic polynomial of this ordinary differential equation of third order is the same as the eigenvalue equation for this system, the equivalent system of first order. Okay? And so I'm actually going to take this blue equation and I'm literally going to compute. This is my A matrix here. This thing here is my A matrix. So I'm literally going to compute A minus lambda I. A minus lambda times the identity matrix is this matrix. Literally this matrix minus, an identity matrix just has diagonals of 1. So maybe I'll write down here, lambda I equals minus lambda 0, 0, 0 minus lambda 0, 0, 0 minus lambda. It's literally a diagonal matrix of plus lambdas. These are plus. Just a diagonal matrix of lambdas, because the identity matrix is diagonal of 1s. If I multiply it by a constant lambda, it's diagonal of lambdas. So A minus lambda I is this A matrix minus this matrix. And so that's minus lambda 1, 0, 0 minus lambda 1, minus A0, minus A1, minus lambda minus A2. Okay, that's not too bad. And now I need to take the determinant of this kind of ugly expression here. Maybe I'll switch colors to orange just to keep things interesting. So the determinant of A minus lambda I. Now, computing the determinant of a big matrix is kind of nasty. It's like a combinatorially complex calculation, but for a 3x3 matrix, it's easy. I'm hoping you remember from high school that it's basically this term times this element times the determinant of this little 2x2 subblock minus this element times the determinant of the 2x2 subblock omitting that row and column, plus this element times the determinant of this little 2x2 subblock. So we can do this easily. It's minus lambda times this determinant, which is lambda squared plus A2 lambda minus A1, which is plus A1. I'm really hoping I don't botch this. Okay, that's the first term. Minus 1 times the determinant of this 2x2 subblock. So these two multiplied together minus these two multiplied together, and that's plus 0 minus A0 is plus A0. And then we also have to add 0 times the determinant of this subblock, but that's just 0, so plus 0. Okay, so that's all the terms for the determinant. And if I didn't mess up, that equals, everything has a minus sign, so I'm just going to say minus, lambda cubed plus A2 lambda squared plus A1 lambda, I already pulled the minus out, so plus A0, all of that. And this determinant has to equal 0. That's the condition. Determinant of A minus lambda I has to equal 0 for lambda to be an eigenvalue of A. So this is literally the equation for lambdas that are eigenvalues of this A matrix. But you'll notice that this is also exactly the equation for the characteristic polynomial of this differential equation. I'll just write it out. Lambda cubed plus A2 lambda squared plus A1 lambda plus A0 equals 0. So this is the eigenvalue equation. The eigenvalue equation for A. And the characteristic polynomial for this differential equation is very similarly lambda cubed plus, you can read it off, plus A2 lambda squared plus A1 lambda plus A0 equals 0. This is the characteristic polynomial, characteristic poly. And of course, these two are completely equal to each other. So that's what I wanted to show you, is that yes, in fact, the roots of the characteristic polynomial are in fact eigenvalues of this matrix A. I can find the eigenvalues of A, and that gives me the roots of my characteristic polynomial. I can find the roots of my characteristic polynomial. Those will give me the eigenvalues of A. And of course, we know that this characteristic polynomial is useful because it tells me specifically the lambdas that give me admissible solutions x of t equals e to the lambda t. So that's going to be a solution of this differential equation if lambda satisfies this characteristic polynomial, or if lambda is an eigenvalue of my A matrix. Very, very useful, very, very simple. So we're going to come back in force looking at this system of equations. What are the eigenvalues of A? What do the eigenvectors of A mean? How do we compute them? How do we solve this system using this math? This is kind of my favorite topic, and I'm very excited to walk you through it. So stay tuned for more. Thank you.